Good afternoon. Thanks to all of you for coming out. Actually, we have some special guests here I'd like to recognize. We have 3 visitors from South Korea, astronomers who are thinking about starting a SETI project in their country. So welcome to you. And also, we have a very special guest whose name is Pierre Schwob, and just today Pierre has agreed to sponsor an ATA antenna. So thank you very much, Pierre, and it's really a pleasure to have you with us. I'm going to go back to my first slide and point out that I want you to remember the funny looking background with that single straight line down a field of snow. I'm going to talk today about the Allen Telescope Array and what it can do for SETI. It's actually the first wide-angle panchromatic radio camera that's ever been built. And that white signal is the kind of thing that we'll be trying to find as evidence of someone else's technology. In fact, it is a truly extraterrestrial signal, having been transmitted by the carrier on board the Pioneer 10 spacecraft on its 30th anniversary, when it was far beyond the solar system and moving just like the stars at sidereal rate on the sky. So that's what we're hoping to find from someone else's technology in the near future. So let me continue and thank Pierre again and move on to this next slide. I think every one of us at the SETI Institute, in one way or another, is involved with this quest to find habitable planets. So far, we know about one, the Earth, and we expect that that's really one among billions, but because it is so difficult to directly detect a pale blue dot like the Earth in orbit around even the nearest stars, we don't yet have the data to verify our expectation. That's one of the things that will be coming in the next decade. We can look forward to results from Corot and Kepler, and we may begin to understand the true statistics of how often a terrestrial type planet does end up orbiting a solar type star. Now, having done that, we have to ask the next question, which is just how close to the Earth does another planet need to be? How similar in order for there to be life on that planet? And because we have absolutely no data on the question, we have 2 prevailing schools of thought today. One is the rare earth hypothesis, which says that although you might find life, microbial life, on other planets, the path that led to complexity on this planet is so tortuous and so improbable that we will never find complex life on any other planets. And then there is the opposite point of view, the life everywhere hypothesis, which says that, yes, perhaps things were difficult in the process of getting to complexity on this planet, but that doesn't mean that's the only way you can end up with complex life. And we don't know what the branching ratio is. If this were a physics experiment, we could run it in the lab and figure out what fraction of the time when you have life on a planet does complexity and even intelligence and technology arise. But this isn't physics. This is astrophysics. This is exploratory science. And so we don't know the answer to the question about life elsewhere. That's what we're trying to find out. And perhaps it will turn out that SETI is actually a shortcut. SETI, I would argue, fits naturally within NASA under the umbrella of astrobiology. SETI is just one of a large suite of observations that can be done in order to try and answer this question. And in fact, SETI may allow us to find habitable planets by using the actions of the inhabitants to provide us with evidence of technology, and therefore the ability to infer the existence of technological inhabitants. And indeed, with the publication of the new roadmap for astrobiology, SETI is once again so designated as an official part of astrobiology, because Goal 7 contains the following text. Human technology and its resultant products and outputs can therefore also be considered as a biosignature, with the added benefit that it might be detected remotely. Thus, although technology is probably much rarer than life in the universe, its associated biosignatures perhaps enjoy a much higher signal-to-noise ratios. Accordingly, current methods should be further developed and novel methods should be identified for detecting electromagnetic radiation or other diagnostic artifacts that indicate remote technological civilizations. So, Goal 7, to determine how to recognize signatures of life on other worlds and on early Earth. SETI is back. We are no longer the four-letter S word that cannot be said in NASA headquarters. And this is really good news, because that means that we can indeed submit proposals for SETI activities under the standard astrobiology call for proposals. So, having said all that, I have to admit that SETI is an incorrect name. It's really a misnomer. The search for extraterrestrial intelligence. Well, we don't know how to find intelligence. Certainly, I'm going to guess that the people in this room are intelligent because they've come to this lecture. But I don't know how to find intelligence at a distance, certainly not the distances to the stars. So what we really should be talking about is the search for extraterrestrial technology. And in that sense, SETI is a very difficult subject. It's got a very left brain and right brain aspects. The left brain thinks about analogs of the kinds of technologies that we use on Earth. Perhaps 21st century Earth on steroids, because most likely any other technological civilization out there is older than we are, more capable. And then the right brain likes to think about all of this science fiction that we enjoyed in the past and wonders about all of the things that we haven't yet invented, all that is probably out there to be known and may, and most likely is, understood by advanced technologies. But how do you go looking for something that you can't even conceive of? This is really unknown territory. So whereas the left brain kinds of approaches looking for technologies that we do understand allows the possibility of conducting and defining searches that have the possibility of having significant null results. When we think about the right brain side of the equation, we just really have no way of quantifying and calibrating what might be necessary. And so this exploration, looking for the stuff that we don't yet understand, actually should become part of astronomy and astrophysics. The best way to look for what we can't conceive of is to conduct a really robust program of observational astronomy, looking with every instrument that we can develop in every way And if by observing the sky we come up with some anomaly, something that our theorists can't explain as a natural phenomena, then we should, as a last resort, consider whether what we've found might not be some manifestation of astroengineering by some distant advanced technology. So when we set out to define the exploratory searches that we're going to do for SETI, we have the same problem that everyone else does about defining what it is that's necessary for a technological civilization to exist versus what's contingent, what happens to be the way we got to be a technological civilization. And this is a really hard concept for everyone, and I was reminded of that by my granddaughter recently. Liao decided to draw a picture for me, and she first started by drawing centipedes and ladybugs, which all had lots of legs. And so when she got around to putting in the aliens for her grandmother, you'll notice that the aliens also have lots of legs. It's just very difficult to tease out with an example of only one what is absolutely necessary to support a technological civilization versus what was contingent. So just need to keep reminding you that aliens do not have to be humanoid. They do have to be intelligent technologists if SETI is going to detect them. We have to try and keep that in mind as we define our search programs. So back to this misnomer. What kind of technology might we detect? Well, Arthur Clarke has told us that anything that's sufficiently advanced, any technology that's sufficiently advanced, will be indistinguishable from magic. When we sit around at conferences or in a bar trying to figure out what's the right technology to go looking for, these are the top 4 ideas. Some sort of power production, transportation, unfortunately war or aggression, and communications. So when you think about magic, that's the right brain sort of the equation. That's the kind of thing that we might be able to detect serendipitously by doing a very good astronomy program. But with respect to the astroengineering artifacts that we can conceive of, the power production, transportation, and war, we've done some small amount of searching for these particular hypotheses. Certainly nothing that would allow us to draw conclusions from our failure to detect them, but interesting searches nonetheless. For example, it's been suggested that an advanced civilization would not let all of their starlight go to waste. They would build a Dyson sphere, as suggested by Freeman Dyson, to capture that power and use it for their own purposes. And so we should look for stars that have infrared excesses. And we've done that. And we've found them. Let me go back. And it turns out that there is an easier explanation that so far fits all of the data for stars with infrared excesses. It's not the radiation from the backside of a Dyson sphere, but rather a disk around the star, either a protoplanetary disk or a debris disk that provides the infrared excesses. So one idea of how to look for some power production that didn't pan out, at least not yet. So another idea then involves the existence of double asteroids. It was suggested a long time ago by Michael Papagiannis that if interstellar colonization takes place, it might be based on very long, slow voyages between the stars, and that any such long, slow ship that enters our solar system might stop off in the asteroid belt to mine a little bit of raw material to keep the voyage going. And therefore Michael suggested looking for asteroids in which there was a small object in orbit around the asteroid. Well, indeed, we have found exactly that, and it turns out to be that the small object is just another piece of rock. Another suggestion having to do with transportation was that perhaps the gamma ray bursts that we see on the sky are the acceleration events of a matter-antimatter annihilation rocket. So you've got this advanced spaceship, and you throw matter and antimatter together, and you get gamma ray photons as the result, as well as a propulsion for your rocket. So there have been attempts to take many of the early gamma ray burst signals and line them up in four-dimensional space-time to see if perhaps there was a consistent trajectory for an interstellar spacecraft. And that didn't work out. How about if you use not how about if you wanted to produce a lot of power by nuclear fission? That was your power source. Then you'd have this really difficult problem of getting rid of the fissile waste from your power production. And as the Yucca Flat dilemma is informing us today, it's really difficult to get rid of that stuff. So one fairly clean green thing you could do with it, if you're an advanced technology, is just throw it into your star. And if you were to do that in sufficient quantities for a significantly long time, then some distant astronomer looking at your star might be startled to see an increase in the intensity of some of the rare earth elements like praseodymium and neodymium as a result of this dumping process. And that would cause the distant astronomer to wonder if maybe they were seeing artifacts of someone's technology. Well, indeed, there's a star called Przybylski's star, which has a very increased rate of production of neodymium and praseodymium and other rare earth elements. But today we don't think that a fissile waste dump is necessary to explain this star. We think that we have a better explanation by the better understanding of the R process formation of elements in such a star. So another idea that hasn't yet panned out. What about if you were sending probes to a distant planetary system, and you realized that your probe might arrive somewhere in the very long process of evolution of life in that planetary system, and you might want to wait around to see if technology develops. Well, if you're going to station yourself in a planetary system for a very long time, you probably want to park your probe in a gravitational minimum, somewhere where it will take the least amount of power to keep your orbit. And if it were our solar system, then and the Earth was the object of interest, then there are 5 Lagrange points relative to the Earth and the Sun. And in fact, the L4 and L5 points are particularly intriguing places for parking a spacecraft for a long period of time. And so we've looked in those directions. We've looked for scattered sunlight off big, bright, shiny objects, and we've done actually a little bit of radar reflectivity observations from those directions as well. And so far what we can say is there probably isn't anything as big and bright and shiny as the Starship Enterprise sitting at the Lagrange points, but we haven't had the sensitivity yet to say anything about small dark probes. So this is an idea which is still in play and could be explored further in the future. Finally, go back to the question of energy production, and suppose that instead of nuclear fission, you actually were doing a nuclear fusion in large quantities to provide your energy needs. Well, in that case, you might have to deal with the fact that nuclear fusion produces some tritium, and you might decide to get that nasty stuff off your planet and have an orbital factory for energy production. And that tritium has a line emission that is the analog of the 21 centimeter spin flip in the hydrogen atom, and the tritium line's at 1512 megahertz, whereas the 21 centimeter 1420 megahertz is the frequency for hydrogen. Now, we've actually done some investigations looking on the sky, scanning for emission at 1512 megahertz. And the reason that this is a significant search, or an interesting thing to do, is that if you found the signature of tritium emission anywhere on the sky except near a recent supernova, you'd have a lot of reason to suggest that that might be someone else's technology, because the half-life of tritium, 12.5 years, is so short that there shouldn't be any extant except near a recent source of production. So these are some of the kinds of things that we've done over the past to look for astroengineering, and to date none have produced any success, but it's also true that none have been systematic enough to yield significant null results. So all of these things perhaps could, in fact, with more sensitivity, turn out to be successful. If indeed you want to think about systematic searches, searches on the basis of which you can calibrate what would be needed to find an Earth analog anywhere in our galaxy, for example, then communications is the thing that we understand, that we certainly do ourselves, and the kind of thing that we could go looking for from other civilizations. So even if you restrict yourself to only looking for electromagnetic radiation as a form of communication, then you're still investigating a gigantic cosmic haystack. It has at least 9 dimensions. There are 3 dimensions of space, 1 of time, 2 senses of polarization for an electromagnetic signal. You don't know what frequency the signal might be transmitted at, and you don't know if there's information encoded, what kind of modulation scheme is being used. And that's important if you're trying to build a match filter to be the most sensitive to that type of signal. And lastly, you don't know how much sensitivity you need, because you don't really know how far away the transmitter might be and how strong it is. So there are 9 dimensions, and you could get all of the first 8 correct, have guessed everything just right, but you could still miss a signal because you didn't have adequate sensitivity. And all of that doesn't even begin to consider more exotic, higher dimensional signals, such as we heard a talk about here a week ago, that considers the quantized orbital angular momentum in a photon, which can carry information and which we're just beginning to investigate at optical and radio frequencies. So a huge haystack to search through just to find electromagnetic signals. And so we've done a number of experiments looking for signals to date, and here's a chart that tries to break those 9 dimensions into a smaller number of dimensions that I can in fact plot. There's a frequency axis which only extends so far, and then optical frequencies are off the chart up to the upper right. The fraction of sky that's been examined, and there's a vertical axis that is some measure of sensitivity. And there are a lot of colored squares in there. In fact, the red one, Project Phoenix, which the SETI Institute just completed a few years ago, a decade-long search to look at 1,000 stars that are like our sun and fairly nearby, and we covered the frequency range from 1 to 3 gigahertz. It's certainly the most sensitive search that's ever been done. It covers more frequency than any of these other searches, and therefore looks pretty good. But the real thing to notice about this chart is not the colored squares, but how empty most of it is. So the point of this chart is really that we haven't even begun to explore the haystack, this really large, vast space. And in order to do a meaningful exploration, what we need is better pitchforks. And that's what we've been doing. We've been trying to build tools that are better suited to this search for extraterrestrial technology. The search for signals of engineered variety has to take place in the presence of an astrophysical background. And what this chart shows is 21 orders of magnitude of frequency over which we can observe the universe. And this is due to Martin Harwitt. From the low frequency cutoff due to the plasma frequency of the interstellar medium, up to the high frequency cutoff where you get pair production against a 3-degree background photons, and therefore an initial photon loses all the information content that it contained. And the vertical axis is the average power flux in watts per square meter per steradian, per patch of the sky. So this average flux is a minimum in the microwave region of the spectrum, and that's where most of our searching has gone on since Frank Drake did the first radio search back in 1960. When you look at optical wavelengths, the background is high. The average background is high because a transmitter on a planet orbiting a star is going to be faced with the radiation from the star, unless you filter it out. And that's the key recently to understanding the fact that spatial or spectral or temporal filtering can in fact radically change this picture of the average background and imply different ways of being able to detect a signal even in the presence of noise. And in particular, if you think about the optical part of the spectrum, Charlie Towns, back in the 60s, told us that we ought to be looking for bright laser flashes from an advanced technology. Now, this is understandable since that's what Dr. Townes won the Nobel Prize for, is inventing the laser and the maser. So why is it that a laser would allow us to have a detectable signal in the presence of stellar photons? Well, it's the fact that the laser pulse can be very, very short. In fact, out at Livermore, there are now petawatt, 10 to the 15 watt lasers that put out a pulse that lasts less than a nanosecond, a billionth of a second. So if you were to count photons very, very quickly with a nanosecond cadence, and you were looking at a nearby star, a star like the Sun, a few hundred light years away, and using a meter-class telescope, the kinds of things that universities can operate, and you counted photons with a nanosecond cadence, then you'd only be expecting in 1 second about 1 million photons from that star into a broad white light filter. Right? 1 million photons from the star in a second. But if you count photons with a nanosecond cadence, then you wouldn't expect any photons from the star in any given nanosecond. Right? So if you get a clump of 10 or 100 photons arriving at 1 nanosecond, you can be pretty sure it's technology rather than astrophysics. And so we have begun Optical SETI recently because it's finally been the case that we can afford photon counters that work that fast. So if you were an extraterrestrial engineer trying to create a signal that you wanted to be captured by a young emerging civilization that's just waking up and using technology to explore its universe, you might decide to craft a signal that looked almost natural, so that when that technology develops the tools to capture that kind of signal, then it will be caught in the net. Your signal, your engineered signal, will be caught along with the natural signals. And it might be some time before anyone realized that that signal was in the database, but eventually it would happen. Here's an example of a pulsar. Very precise radio clocks. The one that you just listened to has a period of about a second. This one is a little faster, this one faster still, and this one, that's a pulsar where the neutron star is rotating about 1,000 times per second, a millisecond pulsar. Now, we have huge databases, and we're always looking for more pulsars because there's a lot of physics that they can probe. And we know that these rotating neutron stars can suffer starquakes, and their moment of inertia gets rearranged in a starquake, and so their period glitches. It changes from one value to another. But we've never found a pulsar whose period changes from one value to a second value, back to the first, back to the second, regularly. Surely, if we found such a thing in our databases, we'd be very suspicious about an engineered versus a natural signal. So this is one type of signal we should be alert for. And again, this falls into the category of doing a really good astronomical research observational program and thinking about anomalies that show up in your databases of sources. Now, the other kind of signal that you might choose to generate to capture the attention of a young technology such as us is a signal which is absolutely artificial, a signal whose characteristics would argue that it cannot be produced by nature. It has to have been engineered. That's the opposite type of signal. And in the case of SETI, over the past 40 some odd years, this is primarily the sort of thing we've been looking for. Some kind of signal that has a time bandwidth product that's close to unity. Now, the uncertainty principle tells us that delta nu, the bandwidth of a signal, times its time duration, delta t, has got to exceed unity. That's the red curve, the limiting boundary curve in this chart. However, technology can produce, often for economic reasons, signals that get very close to that limit, signals that have a very small time bandwidth product. But nature occupies a totally different phase of this graph. Nature is an ensemble emission process. You've got to get a lot of atoms or molecules doing something in order to get a detectable signal. And therefore it isn't possible, at least as we understand in physics today, to get this extraordinarily coherent kind of signal. And therefore, we've used this simple criteria as a way of organizing our searches. When we talk about radio searches, it's frequency compression that we're looking for. Signals that have a very narrow range of frequencies that have excess power. A continuous wave signal, such as the one that I showed you on the very first slide, the carrier from Pioneer 10, or pulses that are narrow and still satisfy this time bandwidth product being small. In the optical part of the spectrum, it's the time compression that we look for, that lots of photons showing up in a very brief pulse, such that you get a high signal-to-noise ratio relative to the average optical background source. And so we've been doing these kinds of searches looking for pretty simple, absolutely knock your socks off, artificial signals. However, as computing gets more affordable, it's possible to go looking for more complex signals with a higher dimensionality. And that's what we're beginning to do today. So here's the difference between astrophysics and technology. The top graph is a hydroxyl, an OH maser, and it is the narrowest line emitter that we know of astrophysically in the radio. And so the top graph is showing 1 megahertz worth of the spectrum, and you can see this double-horned, double-peaked OH emission, which is characteristic of OH-IR star that has an expanding envelope, and the masers are expanding out from the star. In contrast, look at the bottom graph, which is not a megahertz of the spectrum, but only a tenth of a megahertz of the spectrum. Again, you can see 2 peaks, but those peaks are extraordinarily narrow compared to the maser, which never shows features that are compressed beyond, say, 300 hertz. If you expand one of those tiny peaks in the lower graph, so that you have only a kilohertz, 1,000 hertz of data shown, and you look at time versus frequency, so-called waterfall plot, what you can see is one of the sidebands from the Pioneer 10 spacecraft. So I showed you the carrier before. This is actually the information that's being sent down by the spacecraft, and it was so far away and the signal was so faint that the data rate had to be clocked down to only 16 bits per second for the DSN to be able to detect this signal. In fact, we looked at it here with Arecibo, and it's a very detectable signal with that big telescope. But that's the difference between technology and astrophysics. So when we held a series of workshops at the end of the last century to decide what the SETI Institute should be doing for the next couple of decades, we concluded that it still made sense to search for microwave radio signals, but we ought to have our own telescope that was dedicated to SETI. We decided at that time that optical SETI was feasible because the fast photon detectors were affordable, and that got started. And third, we decided that we should try and build an omnidirectional, all-sky, all-frequency, fly's-eye detector that would be sensitive to transient signals. Now, we've gotten the first two going. Number 3 is going to have to wait for Moore's Law and computing to get even cheaper. So up until today, there have been about 100 searches that I can find in the literature, each one picking a small hypothesis and trying to test it. Today on the telescope, we have a search going on at Arecibo, a piggyback Serendip search, which produces data for SETI at home, a fantastic distributed computing phenomenon. There is a small SETI search going on in Medicini, SETI Italia. There are optical SETI searches for targeted stars at both Leuschner Observatory at Berkeley and Lick Observatory in Santa Cruz. And Paul Horowitz and his students at Harvard, having conducted an targeted optical SETI search for 5 years, have now built, because of the existence of arrays of fast photodiodes, they've now built a dedicated optical SETI sky survey scanning telescope. Occasionally there is some activity on Serendip-based boards in Argentina or Australia, and perhaps, as we're hearing today, we can look forward in the future to an experiment in South Korea. So the newest addition to the arsenal of SETI tools is the Allen Telescope Array, which now has 42 dishes. For those of you that haven't been there, it's in Northern California, about a 5-hour drive north from this step here. You can see on Google Earth Mount Shasta and Mount Lassen, the southern two volcanoes in the Cascade chain. And there you can see the Allen Telescope Array just a little bit north of Mount Lassen. It has a site that was developed by the University of California starting in the late 1950s with different radio telescopes, and today it's the site of the Allen Telescope Array. If you look closely, you can see small dots on that lava bed, and these are the 42 telescopes of the Allen Telescope Array. It's a very peaceful, quiet country location. We don't do a lot of advertising. Kind of hard to find. This is the biggest sign that announces the Allen Telescope Array. It's a poster board right near the telescopes. And here's what it looks like from an airplane as opposed to a satellite. These are the telescopes that are today being commissioned. We have a control building that we inherited from the previous BIMA millimeter array on the site. There's an equipment room, there's an electronics lab, and there's a control room with lots of space for students to work during the summer. And if you look at the northern part of the site, you can actually find some more real estate. There are a couple, actually, of 3-bedroom houses for astronomers and their families to use. There is a house for a resident astronomer and a dormitory that sleeps 8 people, or a few more if you use the couches in the living room as well. There's a machine shop, and altogether it's a very well set up bit of infrastructure for supporting astronomy. And this spring we will get organized another tour up there so that those of you that haven't been can see what it's like. The Allen Telescope Array is a partnership between the SETI Institute and the Radio Astronomy Lab at UC Berkeley. The idea is to build a world-class, very large equivalent telescope from small individual telescopes which can be produced by commercial manufacturing techniques. And This is our approach to the next generation of radio telescopes, building them affordably. This telescope offers an enormous frequency range from half a gigahertz to 11 gigahertz. It's the panchromatic part of my title. And within the next few years, the Hat Creek Valley will hopefully sprout 350 of these small antennas, each of which is 20 feet or 6.1 meters in diameter, and each of which is very inexpensive, and the equivalent of a 114-meter telescope can be achieved by combining together 350 dishes. So we've got 350 yet. We only have 42, and those 42 are the result of a fantastic investment in the technology development and first phase of construction by Paul Allen, the co-founder with Bill Gates of Microsoft. And because of Mr. Allen's investment, the telescope bears his name. So we dedicated the first 42 antennas last October, and Paul Allen showed up and pushed a button, and those 42 antennas slewed over to M81 and began taking data. So we've still got 308 to go. The fundraising for that keeps me busy, and one of the reasons that people like Pierre Schwab are so important to the SETI Institute. The idea behind this array is to build it with COTS, consumer off-the-shelf technology, wherever possible, to get the cost down. Historically, radio telescopes have been handcrafted, one of a kind. We need to change that paradigm. We need to change the cost equation for radio telescopes. So here's what they look like. And Tom Pearson, the CEO of the SETI Institute, is fond of calling them the Mr. Potato Head telescope because they really don't look like any telescope that you've seen before. They use offset Gregorian optics. They have a very wideband log periodic feed embedded down at the bottom of the primary, which is the only small area of the primary that's blocked by the large secondary. So we move that secondary down out of the center of the telescope so that it doesn't block very much of the primary. The green in this diagram is a metal shroud that surrounds the feed so that it does not see the warm 300 Kelvin ground, which produces radio emission. And then we cover the feed and the shroud with a radome to keep off the snow and the rain and keep out the birds and nesting bees, which do nasty things to nice high technology equipment. So in the left, it perhaps looks as if the telescope is pointed towards the ground. But in fact, remember, the optics are offset, so the rays are indeed coming in from the upper left, bouncing off the primary, the secondary, and focusing down onto the feed. So this telescope is indeed looking up. The frequency coverage is a combination of a very low noise amplifier. Over on the left picture, you can see a tiny little square, which is less than a millimeter on a side. That is the MMIC low noise amplifier with enormous frequency range, basically from DC to daylight. This chip amplifies all those frequencies. And then the aerial, the thing that collects the radio waves that are focused by the dish. In astronomy, in radio astronomy, we call this a feed. It's that sort of Flash Gordon looking death ray over here on the right, where each of those pennants picks up a different radio frequency. You can think of them as sort of independent dipoles. So the big pennants on the right pick up the lowest frequencies, and the tiny little pennants up near the tip pick up the high frequencies. Now this is old technology made new by the invention at Berkeley of the concept of putting a metal pyramid inside those feed arms and burying inside that pyramid a dewar, a cryogenic dewar at the very small tip end, and behind that a refrigerator from the telecom industries that keeps the dewar cold. So our whole feed cabin is contained within the feed itself, and the signals come off the tip of that log periodic feed and are turned around and immediately go into this cold dewar, which means that you've minimized the noise in the system. And as you can see on the bottom, we've been able to achieve a frequency range of 22 to 1, half a gigahertz to 11 gigahertz. So that's the panchromatic part of the telescope. We take all that signal out of the back end of the feed as an analog signal and amplify it and send it on fiber optics with, again, some more photodiodes from the telecom industry. And we send that signal to the laboratory processing building, and only then do we digitize it. And we don't digitize it in the field because we can't afford to digitize 10 gigahertz worth of data today. But in the future, with Moore's law, our digitizers will get faster and cheaper. So we bring all the analog signal to the lab. We digitize at a rate that we can afford, which today is 100 megahertz times 4 bands. And we plan to ride Moore's law into the future to allow our electronics, our back-end electronics, to get faster and higher bandwidth until such time as Moore's law perhaps runs into the red brick wall that the industry is predicting. But no time soon. We've still got at least 15 more years of Moore's law potential. So the other amazing thing about this array is not only its wide frequency coverage, but its huge spatial coverage. When I use the Arecibo telescope, which is the largest telescope in the world, this is not very much of the sky is seen. So here's the moon and the Andromeda Galaxy, 2.5 degrees across. Here's what Arecibo sees, that tiny little field of view. If I wanted to make an image of the Andromeda Galaxy with Arecibo, it would take thousands of pointings of the telescope to mosaic and build up that image. Arecibo has actually recently put in a focal plane array of 7 receivers, and so it sees a bit more of the sky. But here's what an array that's made of small 6-meter dishes sees. So the field of view of a small telescope is huge. I can get the entire galaxy at one time. And we've built the back-end electronics of the telescope to allow it to do multiple scientific projects. Here is a cartoon that illustrates that by using what's called a spectral imaging correlator, basically a radio camera, my radio astronomy colleagues can make a radio picture, a radio map of that entire field of view with about 18,000 individual pixels. Now, I got tired of drawing lines, so there aren't 18,000 pixels here, but you get the idea. A radio image of the whole area, and each one of those pixels will have 1,024 spectral channels. So you get a very rich data cube when you look at the sky with a correlator and an array of small telescopes. Now, I can do something else at the same time the way this telescope's built. I can have my wide-angle radio camera, which is beginning to produce data. Here's the first image of M31, that Andromeda Galaxy, the very same galaxy that you see here in the optical, is here in the radio a map made at the 21 centimeter hydrogen line, and that map will get more detailed and more sensitive to fainter emission as we add more antennas to the array. Here, by contrast, is an optical image, the first light image from the Pan-STARRS wide field camera, which has the same plate scale as the ATA at 21 centimeters. So optical astronomers are realizing the benefits of wide-angle survey instruments, just as in the radio the Allen telescope array is beginning to exploit that capability. So, as I started to say, there's something else that we can do at the same time that the radio astronomers are making a map of a big region of the sky. And that's the astronomers, SETI researchers, who have individual targets that they want to look at, point source objects that happen to lie in that same field of view. In my case, stars in our own galaxy that are in the foreground of that distant galaxy. That stars that are targets that I want to investigate for SETI can be studied simultaneously by using beamformers. We don't multiply the outputs of the telescopes together. Instead, we add them up with various phase and time delays. So, in effect, we pick out individual pixels within that sky map. And we put special back-end signal processors behind each pixel. In my case, spectrum analyzers with hundreds of millions of spectral channels. In the case of pulsar astronomers who want to do consistent and frequent timing of the arrivals of pulses from a network of millisecond pulsars to study gravitational waves, they can put their back end behind a beamformer that is pointing at the pulsars when they show up in the field of view. So again, here's M31, and as an example of how this sort of thing actually works, I have 3 target stars in that field that come from the best catalog of potentially habitable stars that's been put together by Maggie Turnbull and myself, and a lot more stars from a second-tier catalog where we don't have as good as accurate information about the stars as we do from the Hipparcos catalog. But indeed, these are potentially interesting stars. So you can see that in practice, there are lots of opportunities for this commensal sort of observing. And when the electronics are complete, it should be possible for me to have 8 simultaneous dual polarization beams that I can pick out on the sky at 2 different frequencies for SETI observing. Now, starting with the first observations last October at the dedication ceremony, we looked at M81, and you can see here the 1, 2, 3, 4, 5 stars from my catalogs within the field of view of that object. And on October 11th, we began looking at Hipparcos 48573 as our first SETI target. And as our first observational SETI program with the ATA, we are going to investigate, we're going to use as targets all of the known exoplanet systems that are visible from Hat Creek. So there's one more trick that you can do with an array of 350 small telescopes, and that's the formation of nulls in real time. So not only can you form beams on the sky, but you can form nulls on the sky, areas of the sky for which the telescope has no sensitivity. And the reason you would do this is those are the places on the sky where there is a known satellite that would otherwise corrupt your data. So we can gang up a long series of deep nulls along a satellite track and observe that region of the sky free of interference even when there's a satellite present. So the last thing that we need to do to get the telescope fully working is to finish the electronics. So last June we tore up the equipment room and very rapidly installed a new series of electronics for the ATA-42. You can see at the top we've taken a measurement on the moon and CAS-A, a bright radio source, and we've demonstrated that we have a really good system temperature of on the order of 40 to 45 Kelvin, all the way from half a gigahertz up to about 7 gigahertz. And on up to 10, we have some excess noise that we think we know how to get rid of. But the telescope's functioning. We are actually doing this panchromatic observation across all those frequencies. And given the flexibility of the telescope and all the electronics and different back ends, it shouldn't be any surprise that this is the part of the telescope that we're still working on to get the correlator fully functional, to get the beamformers with the capability to make all of those different beams at different frequencies. So here's our wide-angle panchromatic radio camera. Huge bandwidth in the field, 4 simultaneous frequency channels that can work at any frequency independently throughout the wide bandwidth. The radio camera formed by the correlator, the phased array back ends formed by the beamformers, and a telescope that actually speaks IP protocol. So if you don't like the phased array back ends that we've built, you have another experiment that you want to do with this telescope. You can build a piece of equipment, and as long as it speaks to a computer, as long as it talks IP, it in fact can talk to the ATA. So this is an instrument that we will be able to expand with new back-end processors over time. And the science that we'll be doing with the Allen Telescope Array is all about surveys. That's what this telescope is for. Certainly SETI. SETI targeted surveys, SETI sky surveys. We will, in addition to looking hopefully at something like 1 million targeted stars in the next decade, we'll also scan the inner 20 square degrees surrounding the galactic center. And we'll scan that by moving our phased array beams to something like 3,519 different positions to cover that 20 square degrees. And in doing so, we'll explore somewhere between 4 and 10 billion stars along the line of sight to that dense region. Now, those stars are mostly extremely far away, and so any transmitter that we could detect would have to be enormously powerful, much more powerful than our strongest signal at the Arecibo planetary radar. But this experiment hasn't been done before, and we don't know that there aren't some rare, occasional, strong transmitters, and so we're going to look for them in the place where there are the largest concentration of stars. And then the traditional radio astronomy to be done with the telescope involves surveys as well. Surveys of the nearby hydrogen universe, surveying all the hydrogen out to 1 billion light years, including the dwarf, the big, huge dwarf, huge on the sky, small in mass, but huge on the sky, nearby dwarf galaxies, which have a much higher dark matter to baryonic matter ratio than normal galaxies like the Milky Way. And because we get a map of those galaxies in hydrogen, and we can look at the dynamics and determine the gravitational field, gravitational potential of those dwarf galaxies, looking near the center of the galaxies, looking for how much of a cusp there is. It'll allow us to discriminate amongst various models for dark matter constituents. So this mapping of the nearby hydrogen, really important. Cosmography. It's important because any models of the early evolution and growth of galactic structure in the universe has to come up and match those mapped boundary conditions. So what we see around us today, it's important to know it in detail so that we can constrain models of the early universe. The millisecond pulsar timing network will be used to search for gravitational waves. We'll use this telescope to survey regions of star formation, looking for very large biogenic molecules which have J equals 1 to 0 J equals 1 to 0 lines in the frequency range that we're exploring. And finally, we'll use this telescope to survey the sky for transient radio events, things that happen quickly and only once. We've never been able to do that before. We've never had these wide field instruments in the radio that can look systematically for transients. So the ATA is going to do for the radio sky what the Sloan Digital Survey has been doing recently for the optical sky, and we think that will be an amazing instrument and a really fantastic opportunity for radio astronomy. We can also join in the Lunar Google X Prize, and we've agreed to use the ATA-42 to downlink the mooncasts from any of these private satellites and rovers that actually reach the moon and have to demonstrate that they have satisfied the rules of the competition. We can look forward in the future to building that optical and then radio fly's eye, the omnidirectional SETI search system, which is hung up now because to form all the beams on the sky and process them takes lots of small elements and a great deal of computing power. So this is something that needs to wait for Moore's law to make it more affordable. But in the meantime, if it turns out that you don't need a lot of sensitivity for a fly's eye, if it turns out that there are transient signals out there that are strong enough to detect with a single 6-meter telescope, rather than needing thousands of small elements to detect, then there is something we can do today, and we're doing it. We're doing an ATA-42 fly's eye. So here's a signal that was discovered by data mining the database from the Parkes 13-beam pulsar survey, a very exceptional signal, the likes of which has never been seen before and was only found when there was enough computing power to explore the database looking for very large dispersion measures in the signals. And this particular pulse was found, and it's the only one in that database. If you assume that the large dispersion, dispersion measure indicates an extragalactic distance, then it means that this pulse is strong. Not just a little strong, but knock your socks off strong. So strong that a single 6-meter antenna ought to be able to find it. Now, it's either that dispersion measure is really extragalactic and the signal really is strong, or just possibly this might turn out over time to be one of those engineered signals that I was talking about, almost natural, but with a chirp to imprint this huge dispersion on it to make it look unusual to the astronomers that detect it. But let's assume for the moment that indeed the extragalactic explanation is correct, and therefore this is intrinsically a very strong signal. Well, think about the sky and trying to scan constantly the sky for such strong signals. Well, 42 times 2.5 degrees, which is the field of view of one of the ATA antennas at L-band, that's about 90 degrees. So imagine taking the 42 antennas and arranging them along the meridian from horizon to zenith, and then just letting the Earth rotate overhead. You've actually created a fly's eye that would be sensitive to very strong signals of this nature. And if they're astrophysical, we ought to expect to find many of them. If they're engineered, perhaps they will be rarer. So this is an experiment that we're beginning to start at the ATA today. Well, what about the day after tomorrow? For optical SETI, we'd like to put optical SETI on larger telescopes. Here's an impression, a cartoon if you wish, of the Veritas array, which is now being built to look for the highest energy cosmic rays. And it does so by having these big light buckets with not much imaging quality, but the ability to capture a lot of photons, and a very large array of photodiodes at the prime focus. Now, what they're looking for is air showers caused by these high-energy gamma rays. And so the only events that are recorded from this array at the moment are multiple pixel events. So many photodiodes have to go off before an event is archived. Single events are thought to be noise alone. But suppose you could arrange a fast trigger such that you would capture those single events when the single pixels were from multiple telescopes that triggered at the same time corresponded to the same position on the sky. If you could devise such a trigger, then you'd have a very interesting optical SETI search system. And we're going to look for other ways of piggybacking on large telescopes to be built in the future. Large telescopes, extremely large telescopes, overwhelmingly large telescopes. We'll try and figure out ways to put optical SETI on them. And even the spacecraft that hopefully will not be indefinitely delayed, but will someday launch to look for extrasolar planets. In the radio, we think beyond the omnidirectional sky survey to the day after tomorrow, and we think about the Square Kilometer Array, an international project that is intended to be about 100 times as large as the Allen Telescope Array, and something for which the Allen Telescope Array is in fact an enabler. We think our technology will make this array affordable, and therefore you shouldn't be surprised to see some familiar type telescopes in the background. So this factor of 100 improvement in sensitivity, and maybe something like 250 simultaneous phased array beams looking up at the sky, with which we can do commensal SETI observing, will allow us to look at the many millions of stars that the Gaia spacecraft promises to provide in the next decade for SETI targets. And that factor of 100 in sensitivity means a factor of 10 farther in distance for any particular transmitter. So the Arecibo radar will be detectable out to something like 50,000 light years, more than halfway across the Milky Way galaxy. The Dolly experiment, which has been given some initial study money, may provide us with our first opportunity to do very low frequency SETI observations at frequencies below the ionospheric cutoff of the Earth's atmosphere. So perhaps if this actually flies and the Tsiolkovsky crater in the lunar far side is occupied by these low-frequency arrays, we'll be able to do low-frequency SETI for the very first time. And after that, if indeed the lunar far side is developed and the infrastructure is put in place for some other purposes, certainly we'll never be able to afford it for SETI alone, or even for radio astronomy alone. But if there are multiple reasons to develop that lunar far side, then we'll be able perhaps to take advantage of the treaty in 1979, which defined the far side of the moon as being a radio quiet zone, the shielded zone of the moon, where there should not be any transmitters to interfere with radio astronomy observations. So someday perhaps we will build arrays of telescopes on the moon and do optical SETI from there. But we have to remember also that the far side of the moon is dark half of the time. So that's a place where we could also do optical SETI. And we need to be mindful of the fact that we shouldn't allow our own space exploration to pollute that lunar far side. We should keep this a pristine environment if we're ever going to utilize it for SETI or radio astronomy. So the new pitchforks that we can envision building for SETI are going to be expanding the exploration of the Milky Way galaxy that we can look forward to in the next couple of decades. So here's an image by Seth Shostak, Milky Way galaxy to scale. You can see a tiny little red dot there, which is the region of the galaxy out to about 150 light years that Project Phoenix explored, looking at the 1,000 nearby stars. The Allen Telescope Array in the next decade will expand that sphere to the green that you see. And optical SETI should search out to perhaps 1,000 light years, where dust obscuration will begin to limit its ability to search. And the Square Kilometer Array will expand the radio search farther, out to the realm of 10 to 100 million target stars within 10,000 light years. And we'll also be searching places where there are very strong concentration of stars for extremely strong transmitters, like the Galactic Center. So all of this activity over the next few decades perhaps will be sufficient to allow us to make a detection. And I think that the reason I work on SETI is that, as Phil Morrison once said, SETI is the archaeology of the future. Because of the finite speed of light, any detected signal will tell us about their past, but any detected signal will tell us that we here have a possible long technological future. And that's because unless technologies last for a very long time, SETI will not succeed. So the cartoon on the left shows technology, some measure, on the vertical axis, time on the horizontal axis. For a long time we didn't have any technology. Now it's exponentially increasing. We don't know whether that exponent is going to continue forever or turn over the way most exponentials in nature do. But statistically, if this is the right picture, then the detection that we will make will be of an old, long-lived technology. If, on the other hand, the cartoon on the right is the correct picture, if technology increases and then either destroys itself or turns itself off to be undetectable, then SETI is not going to succeed. For SETI to succeed, on average, technological civilizations and the technology they produce has to have a long lifetime. So if we detect a signal, we can turn that around and say it's possible for the Earth to have a long future. And I think that's a very important message. And that's the reason that I work on SETI, to see if indeed we can show that to be the case. So who's funding SETI these days? Well, not NASA, not since 1993 when Congress terminated the funds for SETI. It's all been funded privately by the SETI Institute, the Planetary Society, various private donors. The National Science Foundation has in fact funded the folks at Berkeley who started SETI at Home to expand that platform to be a generic platform for any kind of scientific distributed computing process. There's been lots of industrial support with in-kind donations of computers and components. NASA actually, through the NASA Astrobiology Institute, has funded a study of M-star habitability, which we started because we want to know whether to put M-stars in our SETI target list. And finally, through the ASTID program, NASA has actually been funding a small project to see if we can use more affordable computing to expand the class of signals that we are sensitive to look for higher dimensional signals than the simple frequency and time compression signals. And so in the near future, we've been talking to NASA about what possibilities there might be for additional SETI involvement. Of course, they could help expand the ATA-42 to 350 or 700. They can expand the number of beams. We can expand the bandwidth with more back-end processing. We can expand the educational programs we do by developing a visitor center at the Allen Telescope Array and creating more curriculum products. And we could build a clone of the ATA in the Southern Hemisphere, and NASA might have reasons for wanting to do this all as a downlink backup system for the DSN. Similarly, in Goldstone, NASA's DSN facility there, outside the gates there is the Goldstone Apple Valley radio telescope, and NASA could put SETI on that telescope. They could build new spectrometers to allow that telescope to conduct a sky survey. They can, again, do educational and scientific outreach there. NASA could fund the automation of Frank Drake's optical SETI survey at Lick. The optical SETI could be pushed into the infrared with new detectors. The Veritas telescope could be equipped with fast triggers for those optical SETI point source signals. Optical SETI could be expanded into the amateur astronomy community with instrumentation that's been prototyped by SBIG. We can go looking for those radio pulses, which may turn out to be neutron-star collisions, or might turn out to be engineered signals with very large dispersion measures. So there's a lot of possibility for near-term activity. I don't know if that will be enough, if all of the searches that we're envisioning for the next few decades will be adequate to detect a SETI signal, because I don't know if there are any signals out there to be detected. So when asked how long we should search or how long it may take, I usually defer again to Phil Morrison and Giuseppe Cocconi and quote the last sentence of the very first refereed SETI paper in a scientific journal, appeared in Nature in 1959. The probability of success is difficult to estimate, but if we never search, the chance of success is 0. So please stay tuned, because we intend to keep searching. Thank you.